Now we're going to apply what we've learned about inverse functions to an exponential function, and we're going to see what happens. So, for example, I have 0 here, 1, 2, 3, 4, and I'm going to find f of x values. Now, we all know, I'm going to make this disappear for a sec. We all know that 2 to the 0 is equal to 1. All right. Then 2 to the 1 is equal to 2. Now, write them both down. I mean, I'm actually interested in both of these at this point, to be honest. I'm going to copy and paste a little bit here. All right, 2 to the 2 would be equal to 4. 2 to the 3 is equal to 8. And I know you want to be lazy and just write 8, but please don't. I'm trying to get at something here. Right, 2 to the 4 is 16, and so on. And it keeps going and going. All right, now for the inverse function, remember, what we do is we revert the process, right? So we take what was our y variable, and in the inverse function, that becomes the x variable. And then what was the x variable in the inverse function becomes the y variable. I want this in Calibri. Hold on. There we go. So we're going to say 0, 1, 2, 3, 4. Okay? And what we've learned is a really important lesson, that if you take the inverse function, if f of x is 2 to the x, then the inverse function of that, the inverse of 2 to the 3, for example, is right here. The inverse of 2 to the 3 is 3. See it right there? Which means we've learned kind of an interesting thing, that namely that the inverse of an exponential function, the inverse function of an exponential function, exponential functions, remember, are the ones where the variable's in the exponent, like 2 to the x. So the inverse function of an exponential function will yield just the exponent, right? So for example, if I had 2 to the inverse function of 2 to the 3, that was 3. I should have boxed that right there. And then if I had the inverse function of 2 to the 7, I know 7 wasn't in here, but look, 2 to the 0 got 0, 2 to the 1 got 1, 2 to the 2 got 2, and so on. Do you see what I mean? You're just going to get the exponent left. So the inverse function of 2 to the 7 would be 7. Or 2 to the 7 million would be 7 million. Whatever that exponent is, that's your inverse function of 2 to that. Okay? All right, now we don't really write it like that because the inverse function itself doesn't really have any meaning. So we needed another way to write it. And what they decided to do was, well, first of all, we already said that this was equal to 3, so let me start with that. Right? We said that the inverse function of 2 to the third is really written as the inverse function of 8, which is 3. But they wanted to give it a name. They wanted to say, you know, you can't just say inverse function of exponential. So the inverse function of an exponential function, that's a lot to say. So they wanted a word that would do that. And the word that they came up with is logarithm. So the logarithm will yield the exponent. Matter of fact, that's what the logarithm is. It's an exponent. It's kind of written a different way, but, or if you will, it undoes the exponent. All right. Okay, so what they did was they decided to write this. Instead of writing f inverse of 8, they wrote it as log base. Now, what was the base? The base of our exponents is 2, so log base 2 of 8 is equal to 3. That's how mathematicians that thought of this decided to write it, because the f inverse notation wasn't really very helpful. So they chose to write it as a logarithm. Logarithm is the name they came up with for it. And they would write the function itself as log base 2 of x, if x was any variable. like in our particular one, we were doing 8. 8 was, and went in there. That's why 8 goes inside that parentheses. So it's the log base 2 of x. That's your f inverse of x. If f of x is 2 to the x, which it was for this entire problem. So this whole problem was talking about f of x is 2 to the x. But what we did here applies to all sorts of variables. And, excuse me, bases, not just base 2. So that's the definition of a logarithm right here. It says, look, if you're going to have a base that's greater than 0, not equal to 1, because remember 1 causes the flat line and we don't want that. But if you have a base bigger than 1 or bigger than 0, you can have a fraction too, like a half will work. And a is greater than 0, then the log base b of a is the number k such that, I gotta type that up, hold on. There we go. It's the number such that b to the k is equal to a. Like that. Okay. And that's kind of the definition of a logarithm. I mean, a logarithm is saying, and I know it's kind of a scary word, but don't be intimidated by it. All it is the inverse of an exponential. So they needed another name for it because it was no good to start writing inverse notation all over the place. So they needed another way to write it, and that's what logarithms are. They are the opposite of an exponential form. Right? So the log base b of a is the exponent on the base b that gives a. And remember, the base of your logarithm is that little number down there. It's the same as your base of your exponential. All right, so let's find these by hand, which is good because I don't have a calculator right now. So we're going to find the log base 2 of 32. So this is going to be equal to some number. And the question is, what number is it equal to, right? Because you want to know, all right, well, if I rewrote it using this definition up here, 2 would be my base. So I'd say 2 to the what power is equal to 32. And if you think about it for a while, you kind of run through the numbers on your calculator, you realize that, oh, it's got to be 5, right? 2 to the 5th power is 32. So 5 is our answer right here. So the log base 32, or base 2 of 32, excuse me, is equal to 5. Actually, I'm going to throw that in there. Right? Now, the steps below are showing why. Honestly, most of the time, you don't bother with this work down here. This is just to kind of, give you instructions for, how did this work? How did this happen? Most of the time, we don't actually write up this work. All right, now let's look over here. We have the log base 5 of 25. So you want to know, all right, what is that? Well, let me think about it. So 5 to the what power would get you 25. That's what you're asking yourself. That's what a logarithm is. It's saying, hey, what power of that base will get me that number in parentheses? It's just written a different way. All right, so that something has got to be, hopefully you see it, 2, right? 5 to the 2 power is equal to 25. So that's our answer. Log base 5 of 25 is equal to 2. And again, most of the time, you don't show the work. You just tell me the answer, it's 2. But this is why it works. All right, let's go down here. Oh, slightly more complicated. Oh, no, these aren't too bad. All right, so log base 6 of 6. Well, let's see here. Again, always be able to rewrite. It really helps. 6 to the what power is equal to 6. Well, that power's got to be 1, right? Awesome. Okay, so the answer then was 1. Let me give it the box treatment here. All right. All right, now what about this one? Let's see here. Because, let's see, 8 to the what power would get me 1? 0, right? Anything to the 0 power is 1. So there we go. It's 0. Cool. All right, so with that, we've learned a couple other lessons that we're going to put right down here. The log base b of b and the log base b of 1. If you're taking the log base b of e, that's like this one over here, right? We did 6 for ours, but there was nothing magical about 6. I mean, you could have done 6 million. It would have worked this way, right? If you have the same base that you have over here in the parentheses, then it must be equal to 1, right? And by the same token, the log base b of 1 will always be equal to 0, always. All right, let me type those up. Hold on. There they are. Log base b of b equals 1. Log base b of 1 is equal to 0. And I wanted to throw in kind of a really important note over here. I don't know if I can box the whole thing, but it's a big deal. Namely that the log base b of 0, all right, hold on one sec. There we go, I got a box around it. Big deal. And the author never really explicitly states it, at least in this portion that I found. But let me just say it here, which is the log base b of 0 is impossible. And you're seeing why right here. I mean, if you take 0, log base 8 of 0, it's equal to 1. If you go with smaller numbers like -1, like the log base 8 of a half or something like that, you'll get -1. But you can't take the log of a negative. It's not possible. Because you can't take 8. Here's why. You can't take 8 to a power and get a negative number. That's not possible. You can't take 8 to a power and get 0. You can take 8 to the 0 power. 8 to the 0 power is 1. That's totally cool. But you can't take 8 to a negative power and get a negative number. Remember that 8 to a negative power, like -1, is actually 1 over 8. It's not 0. It's just a small fraction, right? So it'll never be 0, ever. Okay? So I just wanted to throw those in there for you just to note. So note, I'll put it right here, right? The reason those work is because you can't take 8 or any number to a power and get 0. You can't take any number to a power and get negative. It's not possible, right? Never going to happen. Never. All right, now let's do the common logarithm. A common logarithm is base 10. So when you don't see a base, which, you know, math people are lazy, exactly, yes. So they're very lazy, and so they stopped writing base 10 because base 10 is pretty common. And so it's called the common logarithm. There's another logarithm we'll deal with later. It's called ln. Okay, so log of 10,000. Let's see here. So this is the log of, let me just remind you from, class a long time ago. This is 10 to the 4th. It's however many zeros there are. That's the power you've got. Okay. And this is base 10. They don't say it, but it is. All right. But we already learned right back here, really, that when you have 2 to the power, right, it ends up being the same as the power itself. Like, for example, this one was 2 to the 3rd. We did it right here. 2 to the 3rd. So you'd say, oh, the inverse function of 2 to the 3rd is 3. The inverse function of 2 to the 7 is 7. As a matter of fact, I'll just make a note of it down here. I'll add it into this note. Let's see here. And the log base b of b to the k is k, right? B to the k power is b to the k, right? And because of that, really handy note there, I gotta tell you. So make sure you write that stuff down. Okay, so that's gonna cause this to be 4, because what's gonna happen is 10 to what power gets you 10 to the 4th? Well, 10 to the 4 power gets you 10 to the 4th. So that's how that's gonna work. All right, let's do this one again. Log of 1 over 1,000. So remind yourselves that this is really log base 10. They don't say it, but that's what it is. And let's think about 1 over 1,000 for a second. That's got to be 10 to the, and since it's 3 zeros, it's 3, right? So 10 to the 3rd. Oopsie. 10 to the 3rd. But because it's a fraction, it must be -3. Negative causes the 1 over part, right? And then the 3, the power of 3, makes it 1,000. So this would be -3, according to that rule that we just said, that if it's a log base b, like the log base 10 of 10 to the something, then it's sort of that the logarithms and the exponentials sort of undo each other, right? Right. That's not by accident. That's because they're inverses of each other. And we're out of time on this one. I'll have to pick up right here for the next one. So I'll see you then.